Hello guys, welcome back to Clinically Clear. So today let's cover everything about water, water pollution, water purification, everything. Okay. Now first let's define what is safe and wholesome water. Safe and wholesome water is free from any pathogens, free from any harmful chemicals. The color is less than 15 true color units. It's not truly colorless, but it is almost colorless. Turbidity is less than 1 nephelometric unit, less than 1 NU. It is pleasant to taste. It does not have any bad odor or bad taste. And it is fit for domestic purposes. This is what safe and wholesome water is. Now, before we go to the parameters, see, parts per million is nothing but mg per liter. So, 1 part per million also means 1 mg per liter. They can be used interchangeably. So, now let's look at some chlorine parameters. Some chemical parameters. So, chlorine should be for a contact time of 1 hour, 0.5 parts per million. See, all these are just purely memory based. Just remember a few so that it adds to your answer. Then chlorides, chlorine is different, chlorides is different. Chloride should be less than 250 ppm. If it's more than 250 ppm, the taste changes, and absolutely it should be less than 600 ppm. TDS, that is total dissolved solids or the minerals, should ideally be between 200 to 300, but it has to be less than 500. Nitrates and nitrites, these are indicators of fecal contamination. Nitrate should be less than 50, nitrite should be less than 3 ppm. And there's something known as a nitrate-nitrite ratio, which is the concentration of nitrate divided by the guidelines for nitrate. The concentration of nitrite divided by the guidelines of nitrite, add the two, this ratio, total ratio has to be less than 1. That is also one more thing. Fluorides should be between 0.5 to 1 ppm. If you have too much fluoride, it can cause fluorosis of the teeth. If you have too less, it can cause dental caries. So fluorides have to be in a proper range. And the hardness of water should be 1 to 3 milliequivalents per liter. Okay, these are all how water should be ideally. Now, what are the sources of water? Sources of water, see, you can have rainwater, which is the purest form of water. Rainwater is actually the purest form of water, purest source of water. Surface water, seas, oceans, rivers, canals, impounding reservoirs. What are impounding reservoirs? Basically, you'll have certain catchment areas on both sides where water gets caught and it's flown into an impounding area where you hold the water. So these catchment areas, they catch the water and then they direct it to this impounding reservoirs. They can be natural, they can be man-made impounding reservoirs, like the reservoirs seen in dams. Dams have reservoirs, right? Those are man-made impounding reservoirs. Okay. Now, before we go to it, we should know that for an urban area, about 150 to 160 dppld of water supply is needed, and continuous water supply is always better than intermittent water supply. Why? Because continuous meaning the water keeps flowing, so there is reduced risk of contamination. When water starts accumulating, there's a higher risk of contamination, right? So that is one small thing. Then the third source of water is groundwater. See, groundwater is nothing but wells. Now you can classify wells on various techniques, various bases. Okay. First of all, based on the wall. Pakka well meaning brick wall, kacha well meaning mud wall. Based on the depth, you can classify them into. Before we go to based on the depth, see, identify this. First, you have the surface soil. Then you have the first impervious layer made of small rocks, and you have the and you have the second impervious layer made of big rocks. Okay, so you have water, unconfined aquifer here in between these two layers. You have a confined aquifer here in between these two layers, and another confined aquifer beneath the second impervious layer. So based on depth, you can divide it into shallow wells, which just takes the groundwater above the first impervious layer. These are also known as dug wells. These are the most common in India. They just dig. They don't go all the way below the small rock layer and all. They just dig. Wherever they find water, they'll take it. This is shallow wells. You have another known as deep well that goes all the way below the second impervious layer, below the big rocks, where you have a large amount of water in the confined aquifer. Those are deep wells. Now, what are these natural wells or artesian wells? Most common in India is shallow wells or dug wells. Natural wells or artesian wells, not commonly seen in India. Basically, they go to this middle aquifer. In between the first impervious layer and the second impervious layer, you have a confined aquifer where the water is at high pressure. Okay, what happens is you have a mountain here, you have a mountain here. So what happens is, sorry, you have a mountain here, and then you have an area here, you have a mountain here. So what happens is water accumulates here, and it enters the groundwater, and it comes to the it comes to the water layer in between the two impervious layers. Okay, basically this confined aquifer. And here, because the water is at high pressure, if you dig to this layer, the water rises on its own. It rises all the way on its own. No pump is required in artesian wells. You don't need any pump to bring the water up. It rises all the way on its own due to the high pressure of continuous supply of water in between the first impervious layer and second impervious layer. These artesian wells, they occur naturally. They're not man-made. They're not man-made, and they're not that common in India. Okay, this is based on depth: shallow well, natural well, artesian well, and deep wells. Then based on the design, you have tube wells. What are tube wells? See, what we think of wells is, the ones with that huge opening going deep. They can just be a small tube, like a bore wells, like what's there in bore wells. They can be again shallow, deep. Motorized tube wells, hand pump tube wells. Hand pump is attached manually, you have to pump it up. Motorized meaning it is electronically powered. Now coming to the most important thing, that is something known as sanitary well. What is a sanitary well? Now what are the criteria to call a well as a sanitary well? The well has to be located 100 meters away from any human dwelling, residential area. It has to be 15 meters away from any source of contamination. Then the well should be a brick lined well, pakka well. It should go 6 meters deep, number one. The brick wall above the ground has to come 1 meter above, number two. The opening should have a 3-meter radius. I missed on to write, I didn't write that, but it should have a 3-meter radius. The covering of the well, it should have a cement shed or a covering on top to prevent contamination. Then surrounding the well, throughout the well, around the well, you should have a 1-meter radius cemented platform with a parapet. Parapet is basically you'll have the well here, you'll have a platform surrounding, and you'll have a small, wall like thing called a parapet, and you'll have the sloping, a 1-meter radius platform that is sloping from the edge of the well, cemented platform 1-meter radius with a parapet, and in between you will have a drainage. If there is any water spill, you're getting the water out, there's any spill in the water, it should be directed to the public drainage system. So there should be a pit to direct it to the public drainage system. A hand pump has to be attached somewhere next to the well. There has to be a hand pump to pump the water up in a safe and hygienic manner. The sanitary wells are usually conical in shape to reduce contamination. Generally wells are conical in shape as you go down. They are not perfectly cylindrical, they are conical to reduce contamination. So these are all some criteria to call a well a sanitary well. Properly located, 15 meters away from contamination, 100 meters away from residential area, 6 meter deep, brick lined, brick wall 1 meter above, surrounding the well 1 meter radius cemented sloping platform with a parapet, then connected for a pit to the public drainage system. You have a cement shed or a covering on top, and conical in shape, and a hand pump is present. These are all the criteria to call a well sanitary. Then coming to hardness of water. Now, what is hardness of water? Basically, they are calcium and magnesium salts. When they are present, they are known as hard. They make the water hard. So, how is hardness measured? In milliequivalents per liter. 1 milliequivalent liter of hardness is considered 50 micrograms per liter of calcium carbonate. This is something important. 1 milliequivalents per liter of hardness is equal to 50 mg per liter of calcium carbonate. Now, hardness can be further classified into temporary hardness and permanent hardness. Temporary hardness is due to bicarbonates. Important. Temporary bicarbonates. Permanent is due to nitrates, sulfates, chlorides, mainly sulfates. But remember, temporary is due to bicarbonates. How do we grade the hardness? 0 to 1 milliequivalents per liter, 1 to 3, 3 to 6, and more than 6. 0 to 1 is soft water. Now, you might think soft water is actually good. No. Soft water can actually be corrosive, because when you don't have any calcium and magnesium salts, there is no buffering capacity. So the water can quickly turn acidic. It can become corrosive. So we actually don't want soft water. We want moderately hard water for potable water, for drinking water, for domestic purposes, we want 1 to 3 milliequivalents per liter or moderately hard. We don't want more than that. We don't want 3 to 6 hard or more than 6 very hard water as well. We want moderately hard between 1 to 3 milliequivalents per liter. We do not want totally soft water as well. How do we remove the hardness? See, to remove temporary hardness, you have boiling. What is temporary hardness due to? Bicarbonates, calcium and magnesium bicarbonates. So bicarbonates, when you heat them, what happens? The H2O and the CO2 gets liberated. You have calcium carbonate. Limestone does not dissolve in water, precipitates. You can remove it. Soda ash, you sodium bicarbonate. Soda ash is sodium bicarbonate. You add it. What happens? Just a minute. Yeah, soda ash, sodium bicarbonate. You add it. What happens? There is exchange, right? This is basic chemical reaction. There is exchange. NaHCO3 plus CaCO3. Again, CaCO3 precipitates, calcium carbonate precipitates. Lime, that is calcium hydroxide. You add calcium hydroxide, once again, reaction H2CO2 and CaCO3 precipitates. Basically, all these three, the reactions are the same. You're precipitating calcium carbonate. So that removes temporary hardness, the bicarbonates. What about removing permanent hardness? We need something known as a zeolite method, or an ion exchange method, or a base exchange method. Okay, this removes both temporary as well as permanent hardness. Both temporary as well as permanent hardness. What do we use? We use sodium zeolite or sodium permutate, which is nothing but sodium aluminium silicate. Sodium aluminium silicate, Na2Si2Al2OH2O, that is sodium zeolite or sodium permutate. What happens? Calcium and magnesium, again, exchange. So you get sodium sulfate and calcium and magnesium permutate, which precipitates. Okay, but here sulfates, so even permanent hardness can be removed. But the disadvantage is the zeolite method is so effective, ion exchange method is so effective that it removes all the hardness from the water. We don't want to remove all the hardness because soft water, I told you, is corrosive. So what we do, we get soft water, we again mix it with the raw water, which has some amount of hardness, so that we get the ideal moderately hard water between 1 to 3 milliequivalents per liter. Understood, right? Zeolite method, where you use sodium zeolite or sodium permutate, very effective, but it makes the water totally soft, which we don't want. Next, coming to a very important topic, that is chlorination. Okay, now how does chlorination work? Before we understand chlorination, let's look at chlorine demand. The amount of chlorine required to be added for breakpoint chlorination. What is breakpoint chlorination? I'll tell you. This chlorine demand, the amount, see, there is a water which you want to disinfect. How much chlorine you need to put, that is the chlorine demand. Chlorine demand. This chlorine demand depends on the quantity of water. More the water, more the chlorine. Depends on the contamination. More the contamination, more the chlorine you have to add. Understood? Now coming to what is this breakpoint chlorination? This is breakpoint chlorination. Basically, initially when you add chlorine, you have a water sample, you keep adding chlorine. First, the chlorine gets reduced by reducing compounds. Then the chlorine combines with ammonia. What is ammonia? From contamination. Fecal contamination, organic contamination. Ammonia will be there, right? Organic contamination. So that combines to form chloramine. To chloramine, you add more and more chlorine. What happens? Eventually, the chloramine disintegrates. It disintegrates into what? It disintegrates into free residual chlorine and combined residual chlorine, FRC and CRC. This combined residual chlorine is when the chlorine combines with impurities like aluminium, iron, etc. This free residual chlorine is what is important. After breakpoint chlorination, this free residual chlorine is what we want, because this FRC, it gives rise to hypochlorite ions and mainly hypochlorous ions, which act as a reactive oxygen species, ROS, and they kill the bacteria by oxidation. That is the whole mechanism of chlorine. We want to keep adding chlorine to the water until we reach this breakpoint chlorination, so that we get the FRC. And how much FRC do we need? This target is extremely important. For a contact time of 1 hour, we need 0.5 ppm of free residual chlorine. For when there is an impending outbreak, this is normally just 0.5 ppm chlorine for 1 hour contact time. When there is an impending outbreak, we need 0.7 ppm of chlorine for a contact time of 1 hour. When for swimming pools, 1 ppm of chlorine, free residual chlorine for a contact time of 1 hour. Just remember this is the most important. Okay. Now, how do I calculate this? I calculate it by something known as Horrocks apparatus. So, basically, the amount of bleaching powder required to disinfect a given water sample to reach this target 0.5 ppm 1 hour, that is calculated by Horrocks apparatus. Now, what all does a Horrocks apparatus have? First of all, we have a black cup, one black cup, which has stock solution. Stock solution is when you mix 2 grams of bleaching powder with some amount of water to form a paste. So now you have one black cup with stock solution. You have 6 white cups, numbered 1, 2, 3, 4, 5, 6. Each white cup you will add one. For white cup number 1 you'll add 1 drop of water. For 2 you'll have 2 drops of water, so on and so on. White cup number 6 you'll add 6 drops of water. You have a starch iodine color indicator. So basically what happens, we add the stock solution and we already have the drops of water and we add the color indicator. The first cup to show the color change is N. Whatever it is considered as N. So if the third cup shows, see 3, 4, 5, 6, these are the 4 cups that show color change. That means 3 will become N. 2, 3, 4, 5, 6, these show color change. Then N is equal to 2. So you get to know N from this Horrocks apparatus. And the standard formula is for 455 liters of water, 2N grams of bleaching powder is required. This is 5 star, 10 star, 100 star point. 455 liters of water, 2N grams of bleaching powder according to Horrocks apparatus. Bleaching powder only, not chlorine gas, nothing. 2N grams of bleaching powder for 455 liters of water. Okay. And approximately in rural areas or wherever it is, household areas, we have found that for the given for 1000 liters, approximately 2.5 grams of bleaching powder is required. Don't remember this, that is also okay. But 455 liters of water, 2N grams of bleaching powder. Now, yes, we can most commonly use this bleaching powder because bleaching powder is cheap, easily available. But the problem with bleaching powder is it has only 33% of free chloride. Okay, it has only 33% of free chloride, and you can use high test hypochlorite HTH or perchloron, which has 66% free chloride. Even better, chlorine gas, direct chlorine gas, 100% free chloride. Or if you don't want to do it in the form of a powder, you can do it in the form of a 5% chlorine solution. 5% chlorine solution. We mix 20 liters of water with 4 kg bleaching powder, and then we get 5% chlorine solution. Chlorine tablets, Neri tablets or halazone tablets, 0.5 gram chlorine tablet in 20 liters of water, chlorine tablets. Okay, so these are the different forms of chlorine which you can add. Most commonly bleaching powder, 33%. Perchloron, high test hypochlorite, 66%. Chlorine gas, 100%. 5% chlorine solution, 4 kg powder in 20 liters water. Chlorine tablet, 0.5 gram tablet, 20 liters of water. Understood? Now, I told you this all you'll do to calculate how much is there, you'll add the chlorine, whatever it is. Our target is 0.5 ppm for 1 hour. How do I know? Okay, now this water has 0.5 ppm 1 hour. That to estimate the chlorine levels, I need to do something known as orthotoluidine test. Orthotoluidine test, the principle is orthotoluidine, it turns into a yellow color compound upon reacting with residual chlorine in water. Okay. But it measures total residual chlorine, not just free residual chlorine, but also combined residual chlorine. Now, for us, what's important is FRC, but it is telling you both FRC and CRC, not separately. It's telling you the combined value. FRC plus CRC, both together, it is telling you the total value. Okay. So, it turns yellow upon reacting with this. So, a chloroscope, using a chloroscope, when I measure the intensity of this yellow color, more the intensity of the yellow color, more the concentration of chloride. Basic logic. Now, what is the biggest problem with this orthotoluidine test is we want FRC at 0.5 ppm. So, if there is a water sample with a lot of impurities like iron, aluminium, what will happen? I'll keep adding chlorine, but very less FRC and a lot of CRC. And the CRC is absolutely useless. But still, this will give me a very high total residual chlorine value. So it is giving me a false positive for the chlorine content. So to bypass this, we do something known as orthotoluidine arsenite test, where we add sodium arsenate that removes the FRC, not the CRC. It removes the FRC, free residual chlorine. So now I'm able to separately estimate the CRC. So when I get to know the CRC value by itself, I already know the TRC. I just subtract total residual chlorine from orthotoluidine test minus combined residual chlorine after adding sodium arsenate, orthotoluidine arsenate test. I get to know the free residual chlorine. Understood? Basic logic. So that is how we estimate the chlorine levels. And what is the advantage of chlorination? Chlorination is cheap, and the biggest advantage is residual disinfection. That 0.5 ppm of free residual chlorine, it remains in the water. Future also any contamination, it will take care of it. So residual disinfecting capacity. Only disadvantages, some bacteria like Entamoeba, not some parasites like Entamoeba histolytica, viruses like hepatitis A, they are very resistant to normal levels of chlorine. That's the only disadvantage. Okay, so this chlorination very important. Then fecal contamination or bacteriological survey or biological surveillance for a given sample of water. How will I do? Through something known as presumptive coliform count. Why is it known as presumptive coliform count? Because I am presuming that all feces has coliform bacteria. All human feces has coliform bacteria. So if coliform bacteria I am estimating in the water, I am indirectly estimating fecal contamination. Understood? That is why presumptive coliform count. Which coliform bacteria do we take? E. coli. Why E. coli? E. coli is easy to detect. E. coli is secreted in almost all human feces, and it has a longer lifespan than other pathogenic fecal bacteria. What is the target? Some people might think one bacteria, two bacteria. No, we want absolutely zero E. coli in 100 ml of water. This is the WHO target. Zero E. coli in 100 ml of water is presumptive coliform count. Okay, water is collected by clean catch mechanism. That is basically urine collection. Also, we do clean catch, right, midstream. So clean catch mechanism, in sterile Winchester bottles, we'll collect it, and through multiple tubes method, in sterile Winchester bottles we collect it, and through multiple tubes method or McCartney's chart method, we estimate the most probable number of coliform bacteria in water. Okay, so this most probable number of coliform bacteria in 100 ml water we estimate through multiple tubes method or McCartney's chart method. How do we do it? We take 25 test tubes, each containing liquid broth, McConkey's liquid broth, a growth medium. To each of these test tubes, we add different amounts of water in different titrations, basically different concentration of water. And then we check whether there is any color change, whether there is any gas production. Then what happens? If there is any color change or gas production, it indicates the growth of coliform bacteria, right? So that is how we do McCartney's chart method or multiple tubes method. 25, that's why multiple test tubes, and McConkey's liquid broth. Okay, then false positive. What is false positive? Not just E. coli, but Klebsiella can also end up giving can also end up counting in the can also end up giving a positive result for this presumptive coliform count. So as a confirmatory test, we do something known as Ejectment's test to rule out Klebsiella. That's all. Okay. Then what's important is, how do I know whether this fecal contamination happened nearby very recently or it happened long ago, far away, distant? Streptococcus fecalis in the water indicates nearby, recent fecal contamination. Clostridium perfringens presence indicates long ago, far away, distant fecal contamination. Understood? Streptococcus fecalis, nearby. Clostridium perfringens, long back, far away, distant fecal contamination. Ejectment's test to rule out Klebsiella. Color change gas production, multiple tubes method, McCartney's chart method, Winchester bottle, clean catch, zero E. coli in 100 ml of water. This is bacteriological surveillance. Bacteria, water, fecal contamination, water, presumptive coliform count, biological surveillance. These are all the various titles they can ask in the question. That is it for safe and clean water. I'll cover water purification in a separate video.